60 miles southeast of the big island of Hawaii, something is pushing up through the ocean floor, not slowly, not in the geological sense of slow that scientists usually mean when they talk about volcanoes. This is happening on a timeline that has researchers checking their data twice, then a third time, then calling colleagues they haven't spoken to in years. There is a new volcano being born beneath the Pacific Ocean right now. It has been growing for hundreds of thousands of years, but what geologists are tracking today, what has them genuinely unsettled, is that the process appears to be accelerating. And when you understand what that means, not just for Hawaii but for the ground beneath millions of people's feet, the unease starts to make a lot of sense. To understand what is happening under Hawaii right now, you need to understand what Hawaii actually is. Most people think of it as a chain of tropical islands sitting quietly in the middle of the Pacific. That is one way to see it. Another way, the way geologists see it, is as a series of wounds. Hawaii is what happens when the Pacific tectonic plate, one of the largest slabs of rock on Earth's surface, drags itself slowly over a fixed point of extraordinary heat, rising from deep within the mantle. That point is called a hot spot, and for tens of millions of years it has been punching holes through the ocean floor one after another, like a piece of paper being dragged over a lit cigarette. The result is a chain of volcanic islands and seamounts, stretching nearly 4,000 miles across the Pacific, with the oldest, most eroded remnants to the northwest and the youngest, most geologically active islands to the southeast. The big island of Hawaii sits at the end of that chain right now. It is the youngest major island in the archipelago. It is still growing, and southeast of it, something new is already beginning. The name scientists have given to this emerging underwater volcano is Kamaehuakanaloa, though it was known for decades by a simpler name, Loihi. It sits about 22 miles southeast of the Big Island's southern coast and rises nearly 13,000 feet from the ocean floor. That sounds enormous, and it is, but its summit is still roughly 3,000 feet beneath the surface of the Pacific. It will not break through the waves and become an island for somewhere between 10,000 and 100,000 years, depending on which model you trust and how the next phase of activity unfolds. But here is what makes geologists nervous. Loihi is not behaving the way a quiet, patiently building submarine volcano is supposed to behave. In 1996, the volcano produced a seismic swarm, a rapid sequence of earthquakes, that was unlike anything recorded at a Hawaiian submarine volcano before. More than 4,000 earthquakes struck in a matter of weeks. The seafloor around Loihi's summit collapsed, creating a new pit crater nearly 1,000 feet deep. Hydrothermal vents began venting superheated water, laced with carbon dioxide and hydrogen sulfide, into the surrounding ocean in volumes that killed the microbial communities that had been living there. It was, by any measure, a violent geological event, and it happened at a volcano most people had never heard of, building in an ocean most people never think about, doing something that researchers are still working to fully explain. What makes the situation today even more complex is that Loihi does not exist in isolation. It is part of a system. The entire Hawaiian hotspot system is active simultaneously across multiple points, and the interplay between what is happening at Loihi and what is happening on the Big Island itself is something scientists are watching extremely carefully. The Big Island is home to two of the most active volcanoes on Earth. Kilauea has been erupting more or less continuously for decades, with brief pauses that feel almost like a living thing catching its breath. Mauna Loa, the most massive volcano on the planet by volume, last erupted in 2022 after nearly 40 years of quiet, and that eruption sent lava moving toward populated areas at speeds that left some residents with hours, not days, of warning. What geologists have noticed is that the pattern of volcanic activity across the Big Island has been shifting. The hotspot appears to be migrating, or at least the expression of it at the surface is changing in ways that suggest the plume of heat rising from the mantle is not as fixed as older models assumed. Kilauea's eruption behavior has changed. The nature of the magma coming up, its chemistry, its temperature, its gas content, has been shifting in ways that suggest something is changing in the plumbing system deep below. And deep below is where the truly unsettling part of this story lives. Beneath Hawaii, extending down through the oceanic crust and into the upper mantle, there is a column of anomalously hot rock rising from depths that are difficult to even fully conceptualize. The best current estimates put the base of the Hawaiian mantle plume at somewhere between 1,000 and 2,000 miles below the surface. For comparison, the distance from New York to Denver is about 2,000 miles. The heat driving Hawaiian volcanism is rising from depths comparable to the width of the continental United States. That heat, as it rises, partially melts the rock above it. That partially melted rock, magma, is less dense than the solid rock surrounding it, so it rises further. It pools beneath the crust in vast magma chambers. It fractures and pushes through the crust above. And eventually it reaches the surface, either on the ocean floor at Loihi or through the volcanic vents on the Big Island. The volume of material moving through this system is staggering. Mauna Loa alone contains enough volcanic rock to bury the entire state of California under several feet of lava. The Big Island as a whole is so massive that its weight has literally depressed the ocean floor, creating a moat of subsided seafloor around its base. And all of that volume, all of that mass, all of that heat has been added to the system within the last few 100,000 years. Now geologists are watching Loihi and asking a question that does not have a comfortable answer. What happens when the hotspot's primary focus shifts from the Big Island to the new volcano growing beneath the sea? This is not a theoretical concern. It has happened before. Every island in the Hawaiian chain went through exactly this process. Maui was once the active hotspot island. Before that, Oahu. Before that, Kauai. Each one grew to its maximum size, then the hotspot moved on, and the island began to slowly sink back into the ocean as the oceanic plate continued its northwestward drift, carrying the aging volcano away from the source of heat that built it. The Big Island is currently in the peak phase of this cycle. It is the largest, most volcanically active island in the chain precisely because it is sitting directly over the hotspot right now. But the evidence suggests that this phase will not last indefinitely. The centre of volcanic energy is already beginning to shift toward Loihi. What that transition looks like in practice is one of the things researchers are most interested in understanding. Does the Big Island's volcanic activity simply decrease gradually as Loihi takes over? Or does the transition involve periods of dramatically increased activity as the plumbing system reorganizes itself? The 1996 seismic swarm at Loihi suggested the latter possibility. So did the 2022 eruption of Mauna Loa, which some researchers interpreted as the volcano making one of its periodic, large-scale attempts to maintain relevance in a system that is slowly leaving it behind. The other thing that makes this situation genuinely alarming rather than simply academically interesting is what it means for the people living on the Big Island right now. The southern flank of Kilauea, an area called the Hailina Slump, is one of the largest and most unstable landmass features in the world. It is a section of the volcano's southern side that is slowly sliding toward the ocean. Slowly, in this case, means about 4 inches per year under normal circumstances. But normal circumstances are not always what you get in an active volcanic system. Researchers have calculated that if the Hailina Slump were to fail catastrophically, if a large earthquake or volcanic event caused a significant portion of it to slide into the ocean at once, the resulting displacement of water could generate a tsunami of truly catastrophic scale. Estimates vary, but some models suggest wave heights reaching hundreds of feet along certain Pacific coastlines. This is not considered an imminent threat, but it is considered a real one, and the geological restlessness that has been building in the Hawaiian system over the past few decades has given researchers reason to think about it more seriously than they might have 20 years ago. In 2018, Kilauea's Lower East Rift Zone eruption dramatically altered the landscape of the Big Island's Puna district. Lava consumed entire neighbourhoods. It created new land where the ocean had been. It changed the shape of the island in ways that will be geologically permanent. And it did all of this within a matter of months, on a timescale that was shocking even to scientists who study fast geological processes. What the 2018 eruption also did was provide an unprecedented window into the plumbing system beneath Kilauea. As lava drained from the summit magma chamber to feed the lower rift zone eruption, the summit caldera collapsed in a dramatic series of explosions that were visible for miles. The collapse removed enough material that it effectively reset Kilauea's internal architecture. When the eruption ended and the volcano began to refill, it was doing so into a fundamentally different shaped container than it had before. Researchers are still working through what that means for future eruption behaviour. The preliminary data suggests that Kilauea's eruptive style has genuinely changed since 2018. The eruptions that have followed have been more contained, more focused on the summit region, and have involved lava with slightly different chemical properties than pre-2018 eruptions. Whether this represents a temporary adjustment or a more fundamental shift in how the volcano operates is an open question. And open questions in volcanology are not comfortable things when you have hundreds of thousands of people living on the island in question. Let's step back and look at the broader picture for a moment, because what is happening at Hawaii is not just a local geological event. It is a window into processes that shape the entire surface of the Earth. The Hawaiian hotspot has been operating, with variations in intensity, for somewhere between 80 and 100 million years. In that time, it has produced an enormous amount of the material that makes up the Pacific seafloor. The volume of magma it has generated is difficult to express in terms that feel meaningful, but here is one way to think about it. If you took all of the material produced by the Hawaiian hotspot over its history and spread it evenly across the continental United States, you would be covering the entire country to a depth of several hundred feet. That is the output of a single, relatively modest mantle plume over geologic time, and it is one of dozens of similar features operating around the planet right now. The study of mantle plumes and hotspot volcanism has undergone something of a revolution in the past 2 decades, driven largely by advances in seismic imaging, the same general technology that doctors use for ultrasounds, but applied to the entire planet. By analysing how seismic waves from earthquakes travel through the Earth's interior, geologists have been able to construct increasingly detailed 3-dimensional images of the mantle beneath Hawaii. What those images show is both reassuring and unnerving in equal measure. Reassuring because the plume beneath Hawaii is real, well-defined, and behaving more or less as models predicted. Unnerving because the details of its structure, the way it connects to the deep mantle, the way it interacts with the overlying plate, and the way it appears to be pulsing in intensity over time, are far more complex than older, simpler models suggested. The pulsing is particularly interesting. Evidence from the geological record preserved in the Hawaiian island chain suggests that the hotspot does not produce a constant, steady stream of volcanic output. Instead, it appears to go through periods of higher and lower activity on timescales of millions of years. The current period appears to be one of relatively high activity, which is one reason the rate at which Loihi is building and the intensity of volcanic activity on the Big Island is being watched so carefully. There is also the matter of the chemistry. Volcanoes are not just holes in the ground that lava comes out of. They are chemical factories, processing material from deep within the Earth and releasing it into the atmosphere and ocean. The gases that Hawaiian volcanoes emit, sulfur dioxide, carbon dioxide, water vapor, and a complex mixture of other compounds, have measurable effects on the local environment and, in larger eruption events, on the broader climate. The 2018 eruption's laze, the corrosive haze created when lava enters the ocean, was a visible example of this chemistry in action. Less visible but equally significant are the long-term effects of continuous volcanic emissions on ocean chemistry around Hawaii. The hydrothermal vents at Loihi and elsewhere along the Hawaiian Ridge are continuously altering the chemical composition of the deep ocean in their vicinity, affecting nutrient availability, supporting unique ecosystems, and contributing to processes that ultimately influence ocean chemistry globally. Researchers studying Loihi's hydrothermal vents have found microbial communities unlike anything seen elsewhere on Earth. Organisms that thrive in conditions of high heat, high pressure, low oxygen, and high concentrations of chemicals that would be lethal to essentially every form of surface life. The study of these communities has implications far beyond Hawaii. They are among the best natural analogues available for thinking about the conditions under which life might exist in extreme environments elsewhere in the solar system, places like the subsurface oceans of Europa or Enceladus, where volcanic activity beneath ice sheets might be creating conditions surprisingly similar to what exist right now beneath the Pacific near Hawaii. But back to the immediate question, what exactly is happening right now, and why are geologists alarmed? The alarm, to be precise about it, is not the alarm of imminent catastrophe. No geologist working on the Hawaiian system is predicting that anything catastrophic is about to happen tomorrow or next year. The alarm is more subtle than that, and in some ways more scientifically interesting. What is alarming researchers is that the data they are collecting does not fit neatly into any of the existing models. The rate of seismic activity across the Hawaiian system over the past decade has been elevated compared to historical averages. The pattern of ground deformation, measured with extraordinary precision using satellite-based radar and GPS sensors, shows movements that are inconsistent with a system in a stable, predictable state. The chemistry of gases being emitted from Kilauea and from the seafloor around Loihi has been shifting in ways that suggest changes in the depth and character of the magma sources feeding both volcanoes. None of these observations, individually, would be cause for significant concern, but the combination of all of them, happening simultaneously, across a system that is already understood to be undergoing a long-term transition between its current state and whatever comes next, is what has researchers paying closer attention than usual. There is also a monitoring gap that makes everyone uncomfortable. Loihi sits under nearly 3,000 feet of water. The monitoring infrastructure that researchers can deploy there is limited compared to what they can put on land. The seismic network on the Big Island is sophisticated and extensive. The monitoring of Loihi depends largely on ocean bottom seismometers, research vessel surveys, and occasional remotely operated vehicle dives that can only sample a tiny fraction of the volcano's total surface. The 1996 event demonstrated what can happen when a submarine volcano goes through a major transition. More than 4,000 earthquakes, significant seafloor collapse, dramatic changes to the hydrothermal system, and researchers learned about most of it after the fact, because the monitoring at the time was not dense enough to track it in real time. Since then, monitoring has improved significantly. But the fundamental challenge remains. Loihi is a large, geologically active volcano sitting under nearly 3,000 feet of water, and the cost and difficulty of monitoring it comprehensively is enormous. The Hawaiian Volcano Observatory, which is responsible for monitoring volcanic and seismic activity across the Hawaiian Islands, operates one of the most sophisticated volcanic monitoring networks on Earth. But the resources available for submarine monitoring are a fraction of what is dedicated to the sub-aerial volcanoes on the Big Island. This is a known problem, and efforts are underway to expand the monitoring capabilities around Loihi. But there is an inherent tension between the urgency of knowing more and the practical limitations of what can be deployed and maintained on the deep ocean floor. In the meantime, researchers are extracting as much information as they can from the instruments they have, and what those instruments are telling them is that Loihi is not in a quiet, slowly building phase. It is in a geologically active, dynamically evolving phase. The question is whether the current elevated activity represents a new normal for the volcano as it moves into a more mature stage of its development, or whether it represents the leading edge of a more significant episode of activity. The answer to that question matters enormously, not just scientifically, but practically. The Big Island's southern coast is not densely populated, but it is populated. The ocean between the Big Island and Loihi is a working ocean, travelled by ships and fished by commercial and recreational fishers, and the broader Pacific Basin, connected to the Hawaiian system through tsunami propagation pathways, is home to tens of millions of people living in coastal areas. Understanding what is happening beneath Hawaii right now, in as much detail as possible, is not an abstract scientific exercise. It is a practical necessity. What researchers are hoping to understand better is the nature of the connection between what is happening at Loihi and what is happening on the Big Island. Are they drawing from the same magma reservoir? Are they connected by a continuous conduit system, or are they more independent than they appear? How does activity at one affect activity at the other? These questions are actively being investigated, and the answers are beginning to take shape, but they are not yet complete. What is already clear is that the Hawaiian system is not static. It is not a geological curiosity that can be studied at leisure with no urgency. It is a dynamic, evolving system that is in the process of doing something genuinely new, on a timescale that is fast by geological standards, in a part of the world where the consequences of getting things wrong are not trivial. The emergence of Loihi as an increasingly active geological entity is one of the most remarkable natural processes happening on Earth right now. The slow, inexorable building of a new island from the ocean floor is a process that has happened dozens of times over the history of the Hawaiian chain, but we have never been able to watch it this closely before, with this level of technological sophistication, at this stage of the planet's geological and biological history. There is something genuinely extraordinary about the fact that, right now, as you watch this video and go about your day, a mountain 13,000 feet tall is growing on the ocean floor south of Hawaii. It is doing so through a process of violence and heat and chemical transformation that makes human engineering look trivial. It is doing so on its own geological schedule, indifferent to our monitoring equipment and our models and our alarm, and it will continue to do so for thousands and perhaps tens of thousands of years until it finally breaks the surface and a new island appears in the Pacific, and the chain grows one link longer. That new island will have its own ecosystem, its own weather, its own beaches eventually. Birds will find it. Seeds will arrive on the wind and in the digestive systems of seabirds. Life, as it has done on every Hawaiian island before it, will colonize the new land and begin the long process of making it a place. None of us will see that happen. The timescales are too long, the distance between now and then too great, but the fact that we can watch the beginning of the process, that we can measure the earthquakes and the heat flow and the chemistry of the water above Loihi's vents, that we can understand in real time what is building beneath the Pacific right now, is one of those things that makes being alive in this particular moment feel like an extraordinary piece of luck. The geologists who are watching the system are alarmed. Yes, they are alarmed because the data is telling them things they do not yet fully understand, and in geology, as in medicine, things you do not fully understand deserve serious attention. But they are also, if you speak with them long enough, barely concealing a profound sense of wonder at what they are witnessing. Because what is building under Hawaii right now is not just a geological hazard, it is the future. It is the Earth, doing what it has always done, adding new ground to itself, pushing heat and material from its interior up through its crust, making new land from the raw material of the deep planet. The Pacific plate will keep moving, the hotspot will keep burning, Loihi will keep growing. And somewhere on a timeline that extends far beyond our own lives, a new island will rise from the sea, and the archipelago will be one island longer, and the process will continue, as it has for nearly 100 million years, as it will for millions of years more. That is what is building under Hawaii right now, and understanding it, as fully and as honestly as we can, is one of the most important things we can be doing. So let's talk about what came before, not in the abstract philosophical sense, but in the very literal geological sense, because the story of what is building beneath Hawaii right now cannot be fully understood without understanding what happened to the volcanoes that came before Loihi. What happened to them is one of the more quietly devastating stories in Earth science, and it is also one of the most beautiful, depending on how you choose to look at it. Northwest of the Big Island, stretching in a line that curves gently toward the northwest, and then bends more sharply north toward the Aleutian Islands, there is a chain of islands, atolls, and underwater mountains that most people have never heard of. The northwestern Hawaiian Islands, the Leeward Islands, the Emperor Seamounts. These are the predecessors. The places that were once where Hawaii is now. The volcanoes that were once as active as Kilauea, as massive as Mauna Loa, as geologically furious as anything happening today. And they are, with very few exceptions, either tiny remnants barely above sea level or entirely submerged, dragged beneath the waves by the relentless combination of cooling, subsiding oceanic crust, and the constant erosive work of the ocean itself. Midway Atoll, which many people know from its role in World War II, is one of these. It sits about 1,300 miles northwest of the Big Island, which means it has been carried that far from the hotspot by the movement of the Pacific Plate over roughly 28 million years. What remains of the original volcanic island that was once as large and active as the Big Island is 2 tiny islands and a coral reef, barely above sea level, surrounded by the skeletal remains of a reef system that has been growing upward to keep pace with the sinking of the original volcanic platform beneath. The coral reef is doing something remarkable. As the volcanic rock beneath it slowly subsides, the coral grows upward, building on itself, maintaining a structure at or near the surface even as the foundation sinks. This process, which Charles Darwin correctly identified in the 19th century before geologists had any understanding of plate tectonics, is responsible for all the ring-shaped atolls scattered across the Pacific. They are not what they appear to be. They look like reefs around a shallow lagoon. What they actually are is the visible tops of enormous ancient volcanoes, wrapped in coral that has been growing upward for millions of years to stay near the surface as the rock beneath them sinks. Darwin worked this out from first principles, from observation alone, without any knowledge of hotspots or plate movement or mantle plumes. He saw the pattern, the progression from high volcanic island to low volcanic island, surrounded by a fringing reef to atoll, and he understood intuitively that it represented a sequence of geological aging. That he got the mechanism broadly right, without any of the conceptual tools that modern geology would eventually provide, is one of the more impressive intellectual achievements in the history of natural science. But here is what Darwin could not have known, and what makes the story more interesting than even he realized. The atolls are not just records of geological aging, they are records of biological succession. The ecosystems that develop on a freshly emergent Hawaiian island, the ones colonized by lava-adapted pioneer species, are completely different from the ecosystems that develop on a low, ancient island surrounded by fringing reef, which are in turn completely different from the ecosystems of an atoll. The biological communities are tracking the geological transformation, adapting to each stage, and ultimately disappearing when the rock finally sinks below the surface and the reef can no longer keep pace. Northwestern Hawaiian Islands today represent some of the most pristine marine ecosystems remaining anywhere in the Pacific. The relative lack of human presence there, driven largely by the remoteness that comes from being far from the main Hawaiian Islands, has allowed reef communities to persist in something approaching their natural state. The monk seal that breeds on those islands is found nowhere else on Earth. The coral systems there contain species that have been locally extinct in the main Hawaiian Islands for centuries. These places are not just geological relics, they are biological refugia, preserving ecological communities that have been lost everywhere else, and they will eventually be gone. The seamounts of the Emperor Chain, the oldest portion of the Hawaiian hotspot trail, were volcanically active between 60 and 80 million years ago. They have been sinking slowly ever since. Some of them are now more than a mile below the surface. The biological communities they might once have supported are long gone. Eventually, the same fate awaits everything that is now above the ocean's surface in Hawaii. Not soon, by any human timescale, but eventually. This is the geological context within which Loihi exists. It is not just a new volcano, it is the beginning of a new chapter in a story that has been running for nearly 100 million years. And understanding that context makes the question of what is happening right now much richer and more interesting than the simple alarm headline version of it. Now, there is something about the mechanics of how a hotspot actually works that most explainers skip over, and I want to spend some time on it, because the details change how you understand everything that follows. The hotspot model, the idea of a fixed point of heat in the mantle over which the plate moves, is a simplification. It was a useful simplification when it was introduced in the 1960s, and it captured the most important aspect of what is happening. But the Earth does not actually work with the clean elegance that simplified models imply. The mantle is not fixed. The mantle is itself in motion. The deep, slow convection of the mantle, the process by which heat from the Earth's interior is transported toward the surface over timescales of hundreds of millions of years, means that even the hotspot itself is not perfectly stationary relative to the surface. The Hawaiian hotspot appears to have been drifting slowly southward over geological time, at a rate much slower than the plate above it, but fast enough to complicate the straightforward model of a fixed point and a moving plate. The bend in the Hawaiian Emperor Chain, the place where the chain changes direction from roughly north-south to roughly northwest-southeast, used to be interpreted as evidence of a sudden change in the direction of Pacific plate motion about 43 million years ago. That interpretation turned out to be partially wrong, or at least significantly more complicated than it appeared. More recent analysis suggests that the bend reflects a combination of a change in plate motion and movement of the hotspot itself. The Earth, as usual, turns out to be doing several things at once. The mantle plume beneath Hawaii is also not the simple column of rising hot rock that early models imagined. Seismic imaging has revealed that it has structure, that it is wider in some places than others, that it appears to have variations in temperature and composition along its length, and that it interacts with the overlying plate in ways that affect both the rate and the character of the volcanism at the surface. There is evidence that the plume has periods of higher and lower flux, that the volume of material it delivers to the base of the crust varies over time, and that these variations are reflected in the geological record of the Hawaiian Islands. One of the more striking findings from recent seismic imaging studies is that the Hawaiian mantle plume, at its deepest roots, appears to connect to what geophysicists call a large low-shear velocity province, an enormous region of anomalously slow seismic wave propagation in the deepest part of the mantle, just above the boundary between the mantle and the liquid iron outer core. These provinces, there are two of them, one beneath the Pacific and one beneath Africa, are among the most enigmatic features of Earth's interior. They appear to be thermally and chemically distinct from the surrounding mantle. They may represent ancient oceanic crust that was subducted billions of years ago and has been slowly accumulating at the base of the mantle. They may be something else entirely. Geologists are genuinely uncertain. What is becoming clearer is that the Hawaiian hotspot, and others like it around the world, may be rooted in these deep mantle provinces. The heat that drives Hawaiian volcanism may ultimately be coming not just from the general warmth of the Earth's interior, but from this specific anomalous, poorly understood feature sitting just above the core mantle boundary, nearly 2,000 miles below the Pacific. The line from Loihi's erupting vents to the deepest interior of the planet is longer and stranger than anyone imagined when hotspot volcanism was first described. This matters for understanding the present situation because it means that the Hawaiian system is connected, through its deep roots, to processes that operate on timescales and at depths that are still largely beyond our ability to directly observe or model. The pulsing behavior that shows up in the geological record of Hawaiian volcanism, the periods of higher and lower volcanic output that have been identified from the ages and volumes of the islands in the chain, may reflect changes in those deep mantle provinces, changes in how much material is being delivered to the base of the plume, changes in the temperature or composition of the source region. We are watching the surface expression of something that is happening in a part of the Earth we have essentially no direct access to. The closest thing we have to direct samples from the deep mantle are the xenoliths, pieces of mantle rock that get carried up in erupting magma, and the geochemical signatures preserved in the erupted lavas themselves. Hawaiian basalts have a chemical composition that is distinctly different from other oceanic island basalts, reflecting the unusual nature of their source region deep in the mantle. Reading those chemical signatures is one of the primary ways researchers have been piecing together the story of what is happening at depth. The isotopic ratios in Hawaiian lavas, the proportions of different variants of elements like helium, lead, and osmium tell a story about a source region that has been isolated from the upper mantle for an enormous amount of time, billions of years in some models. These chemical signatures suggest that some of the material being erupted at Kilauea and Loihi today has been sitting in the deep mantle since before complex life existed on Earth's surface. It is being brought to the surface now, erupted into the Pacific for the first time in something like 2 billion years. The idea that a lava flow crossing a road in Hawaii might contain material that was last at the surface before there were animals on Earth, before plants had colonized the land, before most of the continents had assembled into their current configurations, is the kind of thing that stops you if you let yourself actually sit with it. The Big Island is not just a young volcanic island. It is also, in a sense, a museum of ancient Earth chemistry, displaying material from the deep past that has been in storage for geological ages. Let's move to something that connects Hawaii's geological story to a much larger conversation about volcanic systems and their relationship to climate, because this is where things get both more complicated and more important. Volcanoes have a complicated relationship with climate. The popular understanding of this relationship, that volcanic eruptions cool the climate by putting aerosols into the stratosphere that reflects sunlight, is correct as far as it goes. Major explosive eruptions, the kind that produce enormous columns of ash and sulfur dioxide that reach the stratosphere, can have measurable cooling effects lasting 1 to 3 years. The eruption of a volcano in the Philippines in 1991 produced a cooling effect that was measurable in global temperature records for the following 2 years. But Hawaiian volcanoes are not explosive volcanoes in the way that most people imagine when they think of volcanic explosions. They are what volcanologists call effusive volcanoes, which means they tend to produce lava flows rather than explosive ash columns. The magma that feeds Hawaiian volcanoes has a lower silica content and a lower viscosity than the magma that feeds more explosive systems like those found in the Andes or the Pacific Northwest of the United States. Lower viscosity means gases can escape from the magma more easily as it rises, which means pressure does not build to explosive levels in the same way. This does not mean Hawaiian eruptions are gentle. The 2018 eruption demonstrated convincingly that Hawaiian volcanic events can be catastrophic on a local scale. Lava fountains hundreds of feet high, flows moving fast enough to outrun vehicles on damaged roads, entire neighborhoods inundated in days. But the explosivity is of a different character than the big ash column eruptions that do the most damage to the stratosphere. What Hawaiian volcanoes do contribute significantly is carbon dioxide. Kilauea has been one of the largest single-point sources of volcanic carbon dioxide on Earth during its continuous eruption period. The estimates of how much the volcano contributes to the global carbon cycle vary depending on the phase of activity, but even during quiet periods, the emissions are substantial. During major eruptions, they spike dramatically. Now, to be clear about the scale, the carbon dioxide from all the world's volcanoes combined, including subaerial and submarine sources, is a small fraction of what human industrial activity is currently emitting. This is something that climate science has measured carefully and thoroughly. The volcanic contribution to atmospheric carbon dioxide is real, but modest by comparison to what we are adding. This is not a matter of scientific dispute. But the volcanic contribution becomes much more interesting when you look at it over geological timescales. Over millions and tens of millions of years, volcanic outgassing has been one of the primary ways that carbon dioxide gets from the Earth's interior into the atmosphere. And the rate at which volcanoes add carbon dioxide to the atmosphere has varied substantially over geological time, correlating in interesting ways with periods of higher and lower global temperature in the distant past. The slow carbon cycle, the exchange of carbon between the deep Earth and the atmosphere over millions of years, is one of the mechanisms that has kept Earth's climate within habitable ranges over the billions of years since complex life began to evolve. When volcanic outgassing increases, temperatures tend to rise over geological time. When it decreases, temperatures tend to fall. The Earth has mechanisms that push back against both extremes, primarily through chemical weathering of silicate rocks, which removes carbon dioxide from the atmosphere on million-year timescales and eventually returns it to the deep Earth through subduction of carbonate sediments. The hydrothermal vents at Loihi are cooler and more diffuse. They are driven not by fresh magma directly below, but by the interaction of seawater with the flanks of an actively growing volcano. The chemistry is different. The temperatures are lower, and in some ways, the environment at Loihi is thought to more closely resemble the kind of environment in which life may have first originated on Earth, before photosynthesis evolved, when the only available energy sources were the chemical gradients produced by the interaction of volcanic rock with water. This has made Loihi a site of considerable interest to researchers working on the origin of life. Not because life began there, but because the physical and chemical conditions there provide a window into environments that may have been widespread on the early Earth and possibly on other worlds. Early Earth, before the rise of oxygenic photosynthesis roughly 2.4 billion years ago, had an atmosphere and ocean chemistry radically different from today. The ocean was largely anoxic. The crust was hotter and more volcanically active. Hydrothermal systems were probably more widespread and more chemically diverse. The kind of chemistry happening at Loihi today may be a distant echo of conditions that prevailed globally for the first billion or more years of Earth's history. The connection to other worlds is not speculative in the way that might seem at first. Several moons in the outer solar system are now understood to have liquid water oceans beneath their icy surfaces. Europa, a moon of Jupiter, has a global subsurface ocean in contact with a rocky seafloor. Enceladus, a moon of Saturn, is actively venting material from its subsurface ocean into space, and the analysis of that material by the Cassini spacecraft found hydrogen gas, silica nanoparticles, and other chemical signatures consistent with active hydrothermal processes at the ocean floor. Titan, also a moon of Saturn, has a complex organic chemistry, though its surface liquids are hydrocarbons rather than water. If life can exist without sunlight, sustained purely by the chemical energy produced by water-rock interactions, then the habitable zone of our solar system, the range of places where life as we know it might exist, is dramatically larger than it appeared before 1977. It is no longer just a narrow band around the Sun where liquid water can exist on a planetary surface. It potentially includes the subsurface oceans of icy moons billions of miles from any meaningful sunlight. This is one of the reasons that missions to Europa and Enceladus are among the highest scientific priorities in planetary science. The Europa Clipper mission, launched in 2024, will make dozens of flybys of Europa to characterize its ocean and its potential for habitability. Future missions may attempt to drill through the ice or land on Enceladus and sample the material being vented from below. The science that makes those missions meaningful, the science that gives us reason to believe that a sunless subsurface ocean is a plausible place to look for life, was built in part on the study of hydrothermal ecosystems on Earth. And Loihi, sitting quietly beneath the Pacific southeast of the Big Island, growing slowly upward through thousands of feet of ocean water, is part of that story. There is something vertiginous about following the geological story of Hawaii to this point. You begin with fire and rock, and the slow movement of a tectonic plate over a hot spot. You end up at the question of life in the outer solar system. The path between those 2 points is not a detour, it is the direct route, through the geology of the seafloor, through the chemistry of hydrothermal vents, through the biology of extremophiles, through the planetary science of icy moons. Each step follows from the previous one. Each piece of knowledge enabled the next question. That is how science actually works, most of the time. Not in the dramatic moments of individual discovery, though those exist, but in the slow accumulation of connected understanding, where the study of one thing reveals its connections to other things, and those connections open up new questions that turn out to be among the most important questions of all. The Hawaiian Islands, in this sense, are not just a beautiful place or a tourist destination, or even a particularly dramatic geological phenomenon. They are a node in a web of connected phenomena that extends from the deep mantle of the Earth to the outer reaches of the solar system. Understanding them, really understanding them, requires bringing together geology, geochemistry, biology, oceanography, climatology, and planetary science. And even then, the understanding is incomplete, because the science is ongoing, because new instruments and new techniques are revealing things that previous generations of researchers could not see. The summit of Mauna Kea, the highest point in Hawaii, and in many ways the highest point in the Pacific, is covered not just in snow during the winter months but in telescopes. The Mauna Kea observatories are among the most important astronomical research facilities on Earth, taking advantage of the mountain's height, its position above much of the water vapour in the atmosphere, its distance from major sources of light pollution, and the exceptional stability of the air above it. From the summit of a shield volcano built by a mantle plume over millions of years, astronomers study galaxies billions of light-years away, measure the expansion of the universe, characterize the atmospheres of planets orbiting other stars. The same geological processes that pushed Mauna Kea above sea level, that built it to its extraordinary height, that placed it in the middle of the Pacific far from continental weather systems, created the conditions that make it one of the best places on Earth to study the cosmos. The volcanology and the astronomy are connected not just geographically but causally. This is a small example of a larger pattern. The more carefully you look at the natural world, the more connections you find. Systems that appear separate reveal themselves to be coupled. Processes that appear local turn out to have global implications. Phenomena that appear simple turn out to involve mechanisms operating at scales from the molecular to the planetary. Hawaii is an unusually rich example of this pattern, because it sits at the intersection of so many different Earth systems, because its geology is so active and so well studied, because its position in the middle of the Pacific makes it sensitive to changes across an entire ocean basin, and because it has attracted generations of researchers in geology, ecology, astronomy, oceanography, and related fields who have built up an unusually detailed understanding of how this particular piece of the planet works. But it is also, in a sense, a model for how to think about any piece of the natural world. Everything is connected to everything else. The question is always how deeply you want to follow the connections and how far the following will take you. The lava flowing from Kilauea into the ocean tonight, if there is an active flow, is doing something it has been doing for hundreds of thousands of years. It is adding new rock to the island. It is releasing gases into the atmosphere. It is creating new habitat at the edge of the sea, sterile at first, then colonized over years and decades by organisms moving in from surrounding areas. It is a small piece of the planetary carbon cycle, a small contribution to the chemical balance of the ocean, a small addition to the geological record that future researchers may someday read to understand what the climate was like in this place in the early 21st century. It is ordinary, in the sense that it is part of a process that has been going on for an immense span of time, and it is extraordinary in the sense that it is happening right now, that we have the instruments and the knowledge to observe it in real time, to understand what we are seeing, to place it in its proper context in the history of this island, this planet, and this solar system. That is what geology, at its best, offers. Not just an account of what the rocks are made of or how old they are, but a way of situating the present in the deep past, of understanding the current moment as one frame in an immensely long film, of recognizing that the processes shaping the world today are the same processes that have been shaping it for billions of years, operating on timescales that dwarf human history, but that are nonetheless knowable, through patience, observation, and the willingness to ask what the rocks are trying to tell us. Loihi's vents are different. They are associated with a mantle plume system, rather than a spreading centre. The fluids they produce have different chemistry. They are rich in carbon dioxide, iron, and other elements, in proportions that reflect the unusual nature of the magma source below. The microbial communities living at Loihi's vents are adapted to these specific conditions, and they include organisms that have no close relatives in any other marine environment studied so far. Among the most remarkable of these are iron-oxidizing bacteria that form thick rust-coloured mats on the surfaces around the vents. These organisms are doing something very similar to what early life on Earth may have been doing billions of years ago, before the atmosphere contained significant amounts of oxygen, when the ocean was rich in dissolved iron, and the chemical gradients available for biological exploitation were dominated by iron chemistry rather than sulfur or oxygen chemistry. The early Earth's ocean was very different from today's. Before the Great Oxidation event, roughly 2.5 billion years ago, when photosynthetic organisms finally produced enough oxygen to fundamentally change the chemistry of both the atmosphere and the ocean, the world was far stranger. The ocean contained abundant dissolved iron. Volcanic activity was higher. The chemical gradients available for life were different in character, though not necessarily smaller in magnitude. The organisms living at Loihi's vents may be a living window into that world. Not direct descendants, exactly, because 2.5 billion years of evolution separates them from any ancestor that might have lived in the early ocean, but organisms that have retained, through the pressure of their environment, a metabolic strategy that is analogous to what early life may have used. Studying them in detail, understanding the biochemistry of how they extract energy from iron oxidation in a hot, reduced, carbon dioxide-rich environment is one of the more direct ways researchers have of making educated guesses about how life got started on this planet. This is not an idle speculation. The origin of life is one of the central unresolved questions in all of science. We know the ingredients that were available on early Earth. We know the general conditions. We know from the fossil and geochemical record roughly when life appeared. What we do not know still is the specific sequence of events that took simple chemistry and turned it into self-replicating, metabolizing, evolving biology. The gap between chemistry and life is the gap that researchers working on origin of life questions are trying to bridge, and the organisms at Loihi's vents are among the best natural experiments available for thinking about how that bridge might have been crossed. The other place this connects to, the place that takes the story completely off Earth, is astrobiology. The search for life elsewhere in the solar system has increasingly focused on places where liquid water exists in contact with rock, in the presence of a chemical energy source, under conditions that might sustain chemistry, similar to what we see at hydrothermal vents. Europa, one of Jupiter's large moons, has a global ocean of liquid water beneath a shell of ice, kept liquid by the tidal heating generated by Jupiter's enormous gravitational pull. The ocean is in contact with a rocky seafloor. The seafloor is almost certainly geologically active, based on the age of Europa's surface and the amount of tidal energy being dumped into the moon's interior. Hydrothermal vents on Europa's seafloor are not just possible. Most planetary scientists consider them likely. Enceladus, a small moon of Saturn, has already proven that it has an active hydrothermal system. The plumes of water vapor and ice particles erupting from its south polar region contain hydrogen, silica, and organic compounds in proportions that are consistent with hot water, reacting with rock on the seafloor of a subsurface ocean. This is essentially the signature of hydrothermal vent chemistry. We have detected it remotely, from a spacecraft, at a tiny moon 750 million miles from the Sun. When researchers think about what life at those vents might look like, if it exists, they think about it in terms of what we know from places like Loihi. Not identical chemistry, because the compositions are different and the specific conditions vary, but the same general principle: chemical gradients, hot fluid meeting cold, reduced chemicals meeting oxidized ones, and the possibility that biology has figured out how to exploit those gradients the way it has figured out how to exploit every other energy source available on Earth. Loihi is not just a geological curiosity on the floor of the Pacific. It is, in a very real sense, a laboratory for the exploration of the outer solar system, a test case for the principles that researchers are applying when they design missions to look for biosignatures on ocean worlds far from the Sun. The knowledge built up from studying its vent communities, the detailed understanding of how iron-oxidizing bacteria work, what gases they produce, what chemical signatures they leave in the surrounding environment, is directly feeding into the scientific frameworks being used to look for life beyond Earth. Now let's come back to the surface, because there is an aspect of Hawaii's volcanic story that is intensely human, and that does not get the attention it deserves in discussions focused on the grand geological picture. The people who have lived in Hawaii for centuries before any European arrived had a relationship with the volcanoes that was simultaneously more intimate and more sophisticated than most outsiders realize. The geological reality of Hawaii, the fact that the land itself is young and still being made, was not abstract knowledge for the native Hawaiians. It was lived experience embedded in the culture and language and spiritual framework in ways that shaped how they understood their place in the world. Pele, the Hawaiian deity associated with volcanoes and fire, is not simply a mythological character superimposed on a geological process. The stories about Pele encode genuine observational knowledge about how volcanoes behave. Where she walks, the land burns. Where she goes underground, the land rises and fractures. Her movements track the rift zones, the areas of geological weakness along which eruptions propagate. Her conflicts with her sister, the deity associated with the sea, track the interaction between lava flows and the ocean, between the land-building force of volcanic eruption and the eroding, encroaching force of the water. This is not coincidence. These stories developed over many generations of people living on volcanically active land, watching it behave, developing frameworks for understanding it that were embedded in narrative and spiritual practice, because that was the technology available for transmitting complex observational knowledge across generations before writing. The Hawaiian oral tradition preserved, in the form of myth and story and genealogy, a geological and ecological knowledge base built up over roughly 1,500 years of continuous habitation. When modern volcanologists arrived and began studying Kilauea and Mauna Loa systematically, starting in the 19th century, they were not discovering an unknown system. They were bringing one framework for understanding a system that already had a sophisticated indigenous framework applied to it. The two frameworks have had an interesting, sometimes complicated, sometimes productive relationship ever since. The Hawaiian Volcano Observatory was established in 1912, making it one of the oldest continuously operating volcano monitoring stations in the world. Its founders came with Western scientific methods and instruments. They also arrived on an island where people had been watching the same volcanoes for more than a millennium. The knowledge that local residents could provide about historical eruptions, about patterns of behavior, about the geography of lava flow pathways, was invaluable to the early scientific understanding of the system. Today, the relationship between indigenous Hawaiian knowledge and modern volcanology is receiving renewed attention, partly because there is genuine scientific value in traditional ecological knowledge about long-term volcanic behavior, and partly because the communities most affected by volcanic events are predominantly native Hawaiian, and it matters, both ethically and practically, that the scientific institutions doing the monitoring and the communities living with the risk are in genuine dialogue with each other. The 2018 eruption tested that relationship in difficult ways. The communities of Lower Puna that were most severely affected included neighborhoods that had been built on lava flows from the 1955 and 1960 eruptions, land that had been made available for housing partly because it was relatively affordable, and partly because its volcanic history was not well communicated to the people who eventually bought homes there. Many residents had little understanding of the geological hazard they were living with until the lava arrived. This is a failure of communication and of planning, and it is not unique to Hawaii. Volcanic hazard communication is one of the genuinely hard problems in applied volcanology. The challenge is not just scientific. The science is actually reasonably good. The challenge is human. How do you communicate a risk that is real but temporally uncertain, that might materialize in the next eruption or not for another century, to people who are making decisions about where to live and how to invest their resources? How do you do it in a way that does not create unnecessary panic or drive economic harm to communities that depend on those areas for their livelihoods? These are questions that volcanologists, social scientists, emergency managers, and community leaders are actively working on. The 2018 eruption provided a painful and instructive case study in what happens when those systems work imperfectly. What the 2018 event also demonstrated was the extraordinary effectiveness of the monitoring system when it is given the chance to operate. The Hawaiian Volcano Observatory tracked the migration of the eruption from the summit to the lower rift zone in real time. Residents in the affected areas received warnings before the lava reached them. The warnings were not always as early as everyone would have liked, and the evacuation logistics were challenging, but the basic monitoring to warning pipeline functioned. Nobody died from direct lava contact during the 2018 eruption. That is a remarkable fact given the scale of the event. Hundreds of homes destroyed, thousands of acres of land inundated, a major geothermal energy facility threatened. The entire shape of the coastline in one area changed, and 0 direct lava fatalities. That outcome reflects years of investment in monitoring infrastructure, in eruption response protocols, and in community education and preparedness. The lesson, for Hawaii, and for the dozens of other heavily populated volcanic regions around the world, is that the science works when it is properly funded and properly connected to the emergency management and community systems that need to use it. The science alone is not sufficient, but without it, the alternative is much worse. There is a part of the Hawaiian story that requires taking seriously what seem, on first hearing, like almost impossibly large numbers. The things that the geological record suggests are possible at Hawaiian volcanoes, not in terms of the eruptions we normally talk about, but in terms of the largest events the system is capable of, are at the far end of the scale that most people are comfortable thinking about. But they belong in this story, because they are part of what the data is telling researchers about the system they are studying. The Hawaiian Islands are not sitting on flat, stable ocean floor. They are surrounded by evidence of past catastrophic collapse events. Around the base of each major Hawaiian island, on the ocean floor, there are enormous piles of debris, rubble fields that extend for hundreds of miles in some directions, consisting of blocks of volcanic rock ranging from pebble-sized fragments to pieces larger than skyscrapers. These debris fields are the remains of ancient landslides, collapses of the flanks of Hawaiian volcanoes that were not gradual, not the slow sliding that characterizes the Helena slump today, but rapid, catastrophic failures of enormous sections of island mass. The evidence for these ancient collapse events is unambiguous. The debris fields are visible in sonar surveys of the ocean floor. The largest of them are staggering in scale. One debris field on the northern flank of the Big Island contains a single block of rock that is estimated to be roughly the size of Manhattan and several hundred feet thick. It moved from its original position on the volcano's flank to its current location on the seafloor in what the geological evidence suggests was a single rapid event. The geological age of these deposits, constrained by dating of the material on top of them and correlating them with known periods of volcanic activity, suggests that major flank collapse events have occurred multiple times in the history of the Hawaiian chain, roughly once every 100,000 to several 100,000 years. The most recent major event at the Big Island was the Alikatu landslide, which occurred somewhere around 100,000 years ago, and which geologists estimate involved the collapse of roughly 1,000 cubic miles of volcanic material. 1,000 cubic miles of rock, entering the ocean in what was likely a matter of minutes to hours rather than centuries. The energy released by such an event would be almost incomprehensible by any human engineering reference point, and the wave generated by the displacement of that much water would have been unlike anything a human being has ever witnessed. Researchers have found what they believe to be wave deposits, sediment piles that could only have been deposited by an enormous wave on the islands of Lanai and Molokai at elevations of more than 1,000 feet above current sea level. If those deposits are correctly identified and correctly aged, they represent the geological fingerprint of a tsunami generated by the Alikatu event, a wave that crossed the Hawaiian archipelago at heights that are difficult to fully comprehend. Buildings, mountains of water, moving at the speed of a jet aircraft. To be precise about the uncertainty here, there is genuine scientific debate about these deposits. The interpretation that they are wave-deposited rather than produced by some other mechanism has been challenged. The science is not settled in the way that, say, the basic geology of the hotspot system is settled, but the argument that flank collapse events can and do generate enormous tsunamis is not disputed. The mechanism is well understood. The physics is clear. The question is more about the specific timing, scale, and wave run-up of specific past events than about whether such events are possible. They are possible. That much is clear. The Helena slump, the slowly moving southern flank of Kilauea that was mentioned earlier, represents the most closely watched potential site for a future event of this kind in the Hawaiian system. At 4 inches per year under normal conditions, it is the world's most carefully monitored mass movement, and its behaviour is not always normal. In 1975, a magnitude 7.2 earthquake struck the Helena slump and caused the seafloor immediately offshore to drop by several feet. A small local tsunami was generated. Campers on the coast were caught by waves. 2 people died. The event was significant but not catastrophic. What it demonstrated, though, was that the flank of Kilauea is capable of moving rapidly and dramatically in response to seismic events. The 1975 earthquake moved the flank by several feet in the horizontal direction. A larger earthquake, or a combination of seismic and volcanic forcing, could in principle move it by much more. The monitoring of the Helena slump involves GPS receivers, tilt meters, and seafloor instruments that track its position and movement continuously. The data is available to researchers essentially in real time. The hope is that if the slump were to begin accelerating toward a major failure event, the monitoring would provide enough warning to alert coastal communities around the Pacific Basin. Whether that warning would be sufficient, and how coastal communities would respond to a warning of an imminent major Pacific tsunami, is a question that emergency managers spend considerable time thinking about. The Pacific Tsunami Warning System was established after the 1946 Aleutian Islands earthquake generated a tsunami that killed more than 150 people in Hawaii, including schoolchildren in Hilo who had gathered on the waterfront to watch the unusual receding of the sea before the wave arrived. The system has been significantly upgraded since then, and it now includes an extensive network of deep ocean pressure sensors, buoys, and tide gauges that can detect tsunami waves within minutes of their generation and provide warnings to coastal areas before they arrive. But the Helena slump represents a particular challenge for this system. The distance between the slump and some of the nearest populated coastlines, both within Hawaii and on islands like Maui and Oahu, is short enough that warning time could be measured in minutes rather than hours. For a large flank collapse event, the initial wave would reach the nearest coastlines before most warning systems could even confirm what had generated it. This is not a reason to abandon warning systems. It is a reason to invest heavily in public education about tsunami hazards and in land use planning that keeps the highest risk coastal areas from being heavily developed. The latter, in particular, is a conversation that Hawaii has been having for decades with incomplete success, because the economic pressures to develop coastal land are powerful and persistent, and the intervals between major events are long enough that institutional memory fades. Let's stay with the question of scale for a moment, because it connects to something important about how humans process geological risk. There is a documented tendency in human psychology to discount risks that are low in probability but high in consequence, especially when those consequences are so large that they fall outside any personal frame of reference. A person can understand, viscerally and emotionally, the risk of a house fire or a car accident. Those things happen to people they know. The risk is concrete and imaginable. A major flank collapse at Kilauea generating a tsunami that reaches California is not concrete in the same way. It falls in the category of things that are statistically real but emotionally impossible to process. This gap between statistical reality and emotional comprehension is one of the central challenges of communicating geological hazards. It is not unique to Hawaii. It applies equally to the Cascadia subduction zone, which runs along the Pacific Northwest coast of the United States and Canada, and which is capable of producing a magnitude 9 earthquake and associated tsunami on a timescale that, researchers have estimated based on the geological record, ranges from a couple of centuries to a few thousand years. The last major Cascadia event was in January of 1700, a date known precisely because Japanese records preserved the arrival of the resulting tsunami on the far side of the Pacific. It applies to the supervolcano systems like the one beneath Yellowstone, which is a mantle plume hotspot system in some ways analogous to Hawaii, though operating under the very different conditions of continental rather than oceanic crust. The Yellowstone system's eruption history, preserved in the thick layers of ash it has deposited across vast areas of the American West, is a record of events that would have been civilizationally disruptive had they occurred in the current era. The fact that the most recent major eruption was more than 600,000 years ago makes it feel safely distant. The geological evidence that the system is still active, still deforming and producing earthquakes and hydrothermal features, makes the word safely feel somewhat provisional. Hawaii is in this same category of risks that are real, significant, and beyond the emotional range of most people's ability to process. The most honest thing that can be said about such risks is that they exist. They deserve serious scientific attention and emergency planning resources. They should not be ignored or dismissed, but they also should not be allowed to dominate public consciousness in a way that is disproportionate to their probability over any given human lifetime. What Hawaii's geological situation demands is sustained, well-funded scientific monitoring, honest, accessible communication of what is known and what is uncertain, land use planning that accounts for volcanic and tsunami hazard in a systematic way, and emergency response systems that are maintained and updated as scientific understanding evolves. All of these things are happening, to varying degrees. None of them is happening as fully or as well as it could be. The funding for geological monitoring in the United States has historically been volatile, subject to budget pressures and political prioritization in ways that experts in the field find genuinely alarming. The Hawaiian Volcano Observatory has faced funding challenges that have, at various points, constrained its ability to maintain the full density of monitoring it would ideally want. The expansion of submarine monitoring around Loihi that everyone agrees is scientifically desirable has been limited by the cost and complexity of maintaining deep ocean instruments. These are not abstract policy issues. They have direct consequences for how much warning time communities would have in a significant event. The argument for sustained investment in geological monitoring is not a complicated one. The cost of monitoring is trivially small compared to the cost of a major eruption event or a large tsunami. The 2018 Kilauea eruption caused economic damages in the hundreds of millions of dollars and disrupted the lives of thousands of people. A larger event, whether at Kilauea or driven by activity at Loihi or involving a significant Helena slump movement, would cost orders of magnitude more. The return on investment for monitoring, in terms of warning time and better informed emergency response, is extraordinarily high. This is a lesson that keeps being relearned after each major volcanic event, at Hawaii and elsewhere. After the 2004 Indian Ocean tsunami, there was enormous investment in Pacific and Indian Ocean tsunami detection and warning systems. After the 2010 Haiti earthquake, there was discussion of improving seismic monitoring in the Caribbean. After every major event, there is a period of heightened attention, followed by a gradual return to pre-event funding levels as memory fades and other priorities compete for resources. The challenge is to maintain the attention and the investment in the intervals between events, when the political and psychological salience of the risk is lowest and competing demands for resources are highest. This is a governance problem as much as a scientific one, and it does not have a neat solution. But understanding the problem clearly is at least a start. Now I want to talk about something that sits at the intersection of geology and the deep future, because it is one of the most intellectually satisfying aspects of the Hawaiian story, and it brings everything together in a way that I find genuinely beautiful. The Hawaiian archipelago as it exists today is a snapshot, a frozen moment in a process that has been running for nearly 100 million years and will continue in some form for tens of millions of years more. The snapshot we have captured in our brief period of scientific observation shows us a system in an extraordinary moment of transition. The hotspot's primary expression is shifting from the Big Island to Loihi. The Big Island itself is at the peak of its geological life. The northwestern Hawaiian Islands are aging toward eventual submergence, and the Emperor Seamounts, the oldest portion of the chain, are geological ghosts, mountains that barely anyone knows exist, sitting quietly in the deep ocean north of the main chain. The future of this system, projected forward using the same physical principles and the same geological evidence that have allowed us to understand its past, is a story that unfolds over timescales that dwarf our civilization. But it is a story we can tell with reasonable confidence, and it is worth telling. Loihi will continue to grow. The hotspot will continue to add material to it. Based on the average growth rates inferred from the geological record of the other islands in the chain, Loihi will break the surface somewhere between 10,000 and 100,000 years from now. The uncertainty in that range reflects uncertainty in how the transition from Big Island dominance to Loihi dominance will affect the growth rate, as well as uncertainty in the baseline growth rate itself. When Loihi does break the surface, it will initially be a small, barren island, exactly as the Big Island was when it first emerged, and the same process that has made the Big Island into the biologically rich, ecologically complex place it is today will begin to operate on Loihi. The colonization of a new volcanic island is one of the most dramatic natural experiments in ecology. Life arrives before anything that could be called a mature ecosystem exists. The first colonizers are not the organisms best adapted to the eventual climax ecosystem. They are the organisms best at getting there and surviving the initial brutal conditions: no soil, minimal water retention, extreme temperature swings, high ultraviolet radiation, and essentially no shelter from wind. Microorganisms arrive first, blown in on wind currents or carried on bird feathers or in ocean spray. They begin the process of breaking down the bare rock into something that can support more complex life. Ferns, which are extraordinarily effective at colonizing bare lava because of their wind-dispersed spores, arrive next. Then mosses. Then pioneer plants that can survive in conditions no flowering plant could tolerate. Birds arrive while the island is still largely barren, using it as a resting point during long ocean crossings. Some of them carry seeds in their digestive systems, inadvertently planting the first flowering plants on the new land. Over centuries and millennia, the pioneer communities develop into more complex ones. As the soil deepens, water retention improves, and the range of habitable niches expands. The Hawaiian Islands host some of the most extraordinary examples of rapid evolutionary diversification known to science. The Hawaiian honey creepers, a family of birds that descended from a single finch-like ancestor that arrived perhaps 5 to 6 million years ago, diversified into more than 50 species with beaks adapted to different food sources, from long-curved beaks for feeding on tubular flowers to short, stout beaks for crushing seeds. The Hawaiian Silversword Alliance, a group of plants that includes everything from small ground-hugging rosettes to tall, dramatic flowering stalks, all descended from a single tarweed ancestor that arrived from North America. The land snails, the spiders, the crickets, the flies, the flowering plants. The Hawaiian Islands are a laboratory of evolution, demonstrating what happens when small numbers of colonists reach an isolated place with many empty ecological niches and sufficient time for adaptation and diversification to operate. Loihi will go through this same process. It will take a long time, by any human reckoning. But given enough time, the bare lava fields of the new island will support ecosystems as rich and as strange as anything the Hawaiian Islands contain today. Species that do not yet exist will evolve to fill niches that do not yet exist on land that does not yet exist above the surface of the Pacific. This is the trajectory of the Earth's surface, not static, not stable on any timescale that matters geologically, continuously regenerating, continuously losing old land to erosion and subsidence, continuously building new land through volcanism and uplift, continuously shuffling the biological deck as new habitats appear and old ones disappear. The Hawaiian system is one of the most visible, most studied and most striking examples of this process, but it is happening everywhere, at varying rates and in varying modes, across the entire surface of the planet. There is something that researchers working on the Hawaiian system rarely have the opportunity to say publicly, partly because it sounds imprecise in a context where precision is valued, and partly because scientists are generally cautious about statements that exceed what the data directly supports. But if you speak with them informally, if you ask not just what the data shows, but what it makes them think and feel, a consistent theme emerges. The Hawaiian system, in all its complexity and dynamism and scale, has a quality that is difficult to capture in the language of measurement and model output. It feels, in some way, that is hard to make rigorous, purposeful. Not in a supernatural sense, in the sense that it is following rules, pursuing an outcome, doing something that has a coherent internal logic. This is, of course, a projection. Volcanoes do not have purposes. The mantle plume beneath Hawaii does not intend anything. The physics is the physics. The chemistry is the chemistry. But the human mind, encountering something of this scale and this regularity and this extraordinary history, reaches for language that suggests intentionality because that is how we are built. We are pattern-seeking creatures, and the patterns in the Hawaiian system are so clear, so regular over such enormous spans of time that they feel designed even though they are not. The hotspot has been building islands for nearly 100 million years. It will build more. Each island follows the same trajectory: emergence, growth, peak, decline, erosion, submergence. The chain is a visible record of the process, written in rock and water and biology, stretching nearly 4,000 miles across the Pacific. And at its southeastern end, right now, the newest chapter is being written. What is happening under Hawaii right now is the same thing that has always been happening under Hawaii, but we are the first beings in the history of this planet who have been able to watch it with anything like full comprehension. The volcanologists with their seismometers and their GPS receivers and their spectrometers measuring sulfur dioxide plumes. The marine biologists diving to Loihi in remotely operated vehicles, sampling the iron-oxidizing bacteria living at the hydrothermal vents. The geochemists analyzing the isotopic signatures of Hawaiian lavas in cleanroom laboratories. The seismologists building three-dimensional images of the mantle plume from the travel times of earthquake waves. All of them are, in their various ways, reading the same story in the same rock, bringing different tools and different vocabularies to the same extraordinary process. The story they are reading is not complete. There are enormous gaps in understanding. The behavior of the deep mantle is still largely opaque. The connection between deep mantle structure and surface volcanism involves uncertainties that will take decades of additional observation and modelling to reduce. The specific trajectory of Loihi's development, the question of whether the current elevated activity represents a sustained new normal or a transient episode, will not be answerable for years. The possibility of a major Helena slump event remains real, but unquantifiable in any precise probabilistic sense. Science works in this way. It does not provide certainty. It provides increasingly precise uncertainty. It tells you where the edges of understanding are and gives you the best currently available description of what lies within them. The picture of the Hawaiian system that researchers have assembled over the past century of systematic study is vastly more detailed and accurate than what was known in 1912, when the Volcano Observatory was established. It is vastly less complete than what will be known in 2124 if the monitoring continues and the research continues and the data keeps accumulating. The geologist looking at a lava flow in Hawaii is looking at several things simultaneously. The immediate visible object, the rock, its texture, its colour, the way it has flowed and cooled and fractured, the history encoded in it, the chemistry that places it at a particular depth source in the mantle, the age that can be inferred from the decay of radioactive elements within it, the eruption style that left its mark in the shape of the flow. And the context. This rock is part of a system that has been operating for nearly 100 million years, that has produced hundreds of thousands of cubic miles of material, that is in the process right now of shifting its focus to a new volcano growing on the seafloor 60 miles to the southeast. The scale of geology is the thing that most people find hardest to absorb. Not just the spatial scale, though that is impressive enough. A mantle plume rooted nearly 2,000 miles below the surface, connected to an anomalous zone in the deep earth whose origin is still debated, driving volcanism across a chain of islands and seamounts nearly 4,000 miles long. The temporal scale is what truly resists ordinary comprehension. 100 million years. The Hawaiian hotspot was already ancient when the dinosaurs went extinct. It will still be operating in some form when the continents have rearranged themselves into configurations that no one alive today could recognize. Human civilization, in its current form, is perhaps 10,000 years old. That is 1/10,000th of the time the Hawaiian hotspot has been operating. The entire span of recorded human history is geologically invisible. The rise and fall of every civilization, every empire, every technological era that humanity has passed through fits into a geological instant so small that it would not show up as a discernible layer in most rock sequences. And yet here we are, in this geological instant, watching, measuring, understanding, imperfectly but genuinely, what is happening beneath our feet and beneath the ocean, building instruments sensitive enough to detect the ground moving by fractions of a millimetre, drilling into ancient coral to read the chemistry of an ocean that existed before our ancestors were born, sending remotely operated vehicles 3,000 feet down to photograph the iron-oxidizing bacteria living in conditions that might exist on moons of Jupiter. The juxtaposition between the scale of the process and the scale of the observation is one of the things that makes geology both humbling and exhilarating. The mountain that is growing on the ocean floor south of Hawaii does not care about our instruments. It does not know it is being watched. It is building on its own schedule, following its own physics, indifferent to our presence. But we are there. We are watching. And what we are learning about how the Earth works, about how life exploits extreme environments, about how volcanic processes connect to climate and ocean chemistry, and the deep history of the planet, is knowledge that extends far beyond Hawaii. The specific facts of Loihi's growth rate and Kilauea's eruptive behaviour and the Helena slumps movement are important in their own right, for the communities living with volcanic hazard in Hawaii, and for the emergency managers planning for tsunami risk across the Pacific Basin. But the broader knowledge generated by studying the Hawaiian system, the understanding of how mantle plumes work, how hotspot islands form and age and eventually disappear, how life colonizes and adapts to volcanic environments, how the deep carbon cycle connects volcanic activity to climate over geological time. That knowledge belongs to everyone. It is part of the accumulated understanding of the physical world that allows us, as a civilization, to navigate our situation with something more than complete ignorance of the forces shaping it. We are living on a planet whose surface is continuously being remade. The ground beneath most people's feet was, at some point in the geological past, either deep in the earth, or at the bottom of the ocean, or incorporated in the body of some organism that has been dead for hundreds of millions of years. It will eventually be somewhere else, subducted back into the mantle, eroded into sediment, incorporated into new rock. Nothing is permanent. The Hawaiian Islands that exist today will, given enough time, be exactly where the Emperor Seamounts are now, hidden beneath the Pacific, far from the hotspot that built them, slowly dissolving back into the chemistry of the ocean. But right now, they are here. They are alive in the geological sense, active and dynamic and building and eroding and supporting extraordinary communities of organisms and providing a window into the interior of the Earth that we are only beginning to fully use. And 60 miles to the southeast, the next island is starting its slow ascent toward the surface, adding itself to the chain, preparing a place that will not be ready for any human visitor for thousands of generations yet to come. The thing that the Hawaiian system teaches, if you are willing to sit with it long enough to absorb the lesson, is something about the relationship between stability and change. At the human timescale, the islands feel permanent. The ground beneath Hilo feels solid. The summit of Mauna Kea, where some of the world's most sophisticated astronomical observatories sit, feels fixed. But at the geological timescale, everything is moving. The plate is moving northwest at a few inches per year. The hotspot is pulsing in intensity on billion-year cycles. The islands are sinking millimeters each decade as the ocean floor beneath them flexes under their weight. The ocean is rising as ice sheets melt. The coastlines are changing continuously, through erosion and deposition, and lava flows adding new land and storm waves taking it away. Stability, at the geological timescale, is not the absence of change. It is change that is slow enough to look like stability from the inside. The Hawaiian Islands are stable in exactly this sense. They have been in more or less their current form for long enough that they feel permanent to every living thing on them. But the geological clock runs on a different schedule than the biological one, and on the geological schedule, everything happening right now in Hawaii is fast. The eruptions, the growth of loihi, the slow slide of the Helena slump. These are events in a story that has been running for nearly 100 million years, and the fact that they are happening on timescales that a human being can observe directly is one of the things that makes Hawaii, as a geological location, so extraordinary. The researchers who study this system carry that dual awareness. They work on human timescales, with human instruments, within human institutions that have budgets and publication deadlines and grant cycles. And simultaneously they are trying to understand a process that operates on a timescale that makes all of that feel almost comically brief. The ability to hold both perspectives at once, the human and the geological, the immediate and the immense, is one of the things that makes the best geological scientists so interesting to talk to. They have a kind of temporal depth perception that most people lack, a capacity to see the landscape not just as it is, but as it is becoming, on a schedule that no individual will ever live long enough to witness completing itself. What is building under Hawaii right now is many things simultaneously. It is a geological hazard that deserves serious, sustained scientific attention and honest public communication. It is a laboratory for understanding the deep earth, the origin of life, the colonization of extreme environments, and the principles that might eventually guide the search for life beyond our planet. It is a record of nearly 100 million years of planetary history, written in rock and chemistry in the ages of islands. It is the future of the Hawaiian archipelago, the next link in a chain that has been growing since before there were flowers on Earth. And it is a reminder of the kind that geology provides better than almost any other discipline, of the extraordinary privilege of being alive in a moment when we have the tools and the knowledge to understand what is happening at such scales and such depths. The mountain growing under the Pacific does not need us to witness it. It was building long before there were eyes to see it, and will continue long after any eyes currently living have closed. But we are here, and we are watching, And what we are learning is not just about Hawaii. It is about the planet we live on, how it works, how it has always worked, and what it is in the process of becoming. That knowledge, imperfect and incomplete as it is one of the most remarkable things our species has managed to accumulate. And the Hawaiian system, in all its geological complexity and violence and beauty, is one of the places where that accumulation continues.